Good morning, students. In this video, I am going to discuss about close packing in crystalline solid. That is, today's topic is close pack structure of crystalline solid. You know, in crystalline solid, the particles are very closely attached with each other. Okay, and there are some empty or vacant spaces also exist among the sphere of crystalline solid, and these vacant spaces are known as voids or holes. Okay, so in solid the constituent particles are close packed, leaving behind minimum vacant space. And one more thing I want to inform you that here all the particles of crystalline solids are assumed as a solid hard sphere. Okay, that is identical hard sphere. Now see, close packing in crystalline solid can be represented in three different ways. One is close packing in one dimensional dimension, close packing in two dimension, and close packing in three dimension. Okay, among these different types of close packing, the actual close packing that are exist in crystalline solids, which is three dimensional close packing. This is the real close packing. Okay, and for simplicity here it is showing one dimensional close packing, two dimensional close packing. Okay, so first see one dimensional close packing or close packing in one dimension. It look like this. Okay, the particles are arranged only in one direction. Okay, so there is only one way of arrangement of sphere in one dimensional close packed structure, that is to arrange them in a row and touching each other. And in this arrangement you can see each sphere is in contact with two nearest neighbors. That's why quotient number of each sphere. Okay, each quotient number of each sphere is 2. And what is quotient number? The number of nearest neighbors of a particle is called coordination number. The number of nearest neighbors of a particle is called coordination number. Okay, and in one dimensional close packing, each sphere is attached with two nearest neighbors. That's why coordination number of each sphere is 2 in one dimensional close packing. Now see two dimensional close packing. You can obtain two dimensional close packing or close packing in two dimension from one dimensional close packing. Okay, so two dimensional close pack structure can be generated by placing the rows of close packed sphere. And there are two different ways of obtaining two dimensional close packing from one dimensional close packing. So first one is like this, square close packing, and second one is hexagonal close packing. Okay, so there are two different types of close packing in two dimension. One is square close packing. It look like this. This is square close packing and this is hexagonal close packing. Okay, so in square close packing, square close packing, the second row may be placed in contact with first row. One in two dimensional square close packing, the second row may be placed in contact with the first one, such that the sphere of second row are exactly above those of the first row. It is clear, I think it is clear from this figure. Okay, the sphere of second row are exactly above those of the sphere of first row. Okay, and this is in square two dimensional square close packing. The sphere of second rows are the sphere of second row are exactly above those of the first row. The sphere of the two rows are aligned horizontally and as well as vertically. And if we call the first row as A type, if we call the first row as A type, then the second row being exactly same as the first row, so it is also a type. Similarly, we may place more rows to obtain a type arrangement. Okay, so two-dimensional square close packing is also known as a type arrangement, because in two-dimensional square close packing each rows are identical. Okay, you can see they are identical in horizontally and vertically in both direction. And now see two-dimensional hexagonal close packing. One more thing, in two-dimensional square close packing is sphere. Each sphere is directly attached with four nearest neighbors. That's why this in this arrangement the coordinate number of each sphere is 4. Okay, now see two-dimensional hexagonal close packing. It is given at the right. This is two-dimensional hexagonal close packing. In this type of arrangement, it is clear from this figure that is all layers or rows are not identical. Okay, first rows and second rows are not identical, but first and third are identical, and second and fourth are identical. Okay, so first rows is first layer is A type, second layer is B type, third layer is also A type, fourth layer is also B type, and fifth layer is also A type, like this. So AB type arrangement. Okay, and how this two-dimensional hexagonal close packing is obtained from one-dimensional close packing, it is explained here. See this point, and this one I have already told, that is coordinate number of square close packing. Two-dimensional square close packing coordinate number is 4, because each sphere is in contact with 4 of its neighbors. Thus the two-dimensional in two-dimensional square close packing the coordinate number is 4. Okay, and here it is written, it is also known as square close packing in two dimension, because this is because if the center of four immediate neighboring sphere, if the center of four immediate neighboring sphere are joined, a square is formed. Hence this packing is called square close packing in two dimensional. It is about two dimensional square close packing. About this, coordinate number is 4, and this is known as square close packing. This is because if the center of these four immediate neighboring sphere are joined, a square is formed. Okay, hence this packing is known as square close packing in two dimension. Now see hexagonal close packing in two dimension, that is this figure V. Okay, so so what is hexagonal close packing in two dimension? The second row may be placed above the first one in a staggered manner such that the sphere fit in the depression of first layer. That is, the sphere of second row is placed in the depression of first layer. Okay, so in the second, if the second row is placed in the depression of first row, then you will get two-dimensional hexagonal close packing. Okay, if the arrangement of sphere in the first row is called A type, the one in the second row is different and may be called B type. And when the third row is placed adjacent to the second in a staggered manner, its sphere are aligned with those of the first layer. Hence this layer is also A type, that is third layer is also A type. Okay, and the spheres of similarly placed fourth row will be aligned with those of second row, that is B type. Okay, hence this arrangement is AB type arrangement. The hexagonal two-dimensional hexagonal arrangement is also known as AB type arrangement. In two-dimensional hexagonal close packing, the particles of second row or third row or fourth row, they are placed in the depression of in the they are placed in the depression of previous rows. Okay, you can see this particle is placed in the depression of first rows. Okay, all this sphere, and in two dimension square close packing, each sphere is just above of the previous layer. Okay, see, so in this arrangement, in two dimensional hexagonal arrangement, there is less free space, and this packing is more efficient than two-dimensional square close packing. And each sphere is in contact with each sphere is in contact with six neighbors. And the two-dimensional hexagonal close packing, in two-dimensional hexagonal close packing, the coordination number is 6, because in two-dimensional hexagonal close packing, each sphere is directly attached with six nearest neighboring. Okay, so coordination number is 6 in two-dimensional hexagonal close packing, and here one hexagon is obtained, that's why it is known as hexagonal close packing. Okay, so in two-dimensional close packing, the coordination number is 6, and the center of these six sphere are at the corner of a regular hexagon. Hence this packing is called two-dimensional hexagonal close packing, and it can be seen in the figure 1.14b, that in this layer there are some void or empty spaces, and these voids are called triangular space or triangular voids in two dimension. And the triangular voids are of two type. One is in one rows, the apex of triangles are pointing downward, and in the next layer it is upward. Okay, now the see close packing in three dimensional, and this is the real or actual close packing in crystalline solid. And one thing I want to mention you, it is very difficult to explain this type of close packing without proper three-dimensional structure. Okay, because our this page is two-dimensional page. Okay, and this picture also two-dimensional. Within two-dimensional picture, it is very difficult to represent three-dimensional drawing. However, it is showing here, you can see this is three-dimensional close packing, and you can obtain three-dimensional close packing from two-dimensional close packing. Okay, all real structure are three-dimensional structure, and they can be obtained by stacking two-dimensional layer one above the other. In the last section, we have discussed close packing in two dimension, which can be of two types: square close packing and hexagonal close packing. Okay, and three-dimensional close packing. Now see three-dimensional close packing. I have told that three-dimensional close packing can be obtained from two-dimensional close packing. So first see three-dimensional close packing from two-dimensional square close packing from two-dimensional square close pack layer. Okay, and this is like this sim cubic arrangement. This arrangement is obtained from the two-dimensional square close packing. Okay, and this type of arrangement is known as simple cubic lattice, and this arrangement is also a type arrangement. Okay, so three dimensional close packing from two-dimensional square packed layer. While placing the second square close packed layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. The second layer is placed above the first layer. The second layer, this one is placed above the first layer. Okay, exactly above the first layer. The second layer is placed over the first layer such that the sphere of the upper layer are exactly above those of first layer. In this arrangement, sphere of both the layer are perfectly aligned horizontally as well as vertically. Okay, so similarly, we may place more layer one above the other. We place more layer one above the other. If the arrangement of sphere in the first layer is called A type, if the first layer is A type, then second layer is also A type, and third layer is also A type, fourth layer is also A type. Okay, so in this arrangement, if the arrangement of sphere in the first layer is called A type, all the layers have the same arrangement. Thus, this is called AAA type arrangement. Okay, and the lattice thus generated is simple cubic lattice. Okay, so the lattice generated is known as simple cubic lattice, and this simple cubic lattice is obtained from two-dimensional square close packing, and the unit cell is primitive unit cell. Okay, now say three-dimensional packing from two-dimensional hexagonal close packing. Next, three-dimensional close packing from two-dimensional hexagonal close packing from two-dimensional hexagonal close packing. Okay, so three dimensional close packing from two-dimensional hexagonal close pack layer. Three-dimensional close pack structure can be generated by placing layer one over the other, and there are two types of close packing can be obtained from two-dimensional hexagonal close packing. One is known as three-dimensional hexagonal close packing, another is three-dimensional cubic close packing. Okay, these two type of close packing can be obtained from two-dimensional hexagonal close packing. So three-dimensional close packed structure can be generated by placing layer one over the other, placing second layer over the first layer, placing second layer over the first layer. Let us take a two-dimensional hexagonal close pack layer A. Place a similar layer above it such that the sphere of second layer are placed in the depression of first layer. Okay. Since the sphere of the two layers are aligned differently, let us call the second layer as B, and it can be observed from the figure 1.16 that not all the triangular voids of the first layer are covered by the sphere of second layer, and this gives rise to different arrangement. Okay, whenever a sphere of second layer is above the void of first layer, a tetrahedral void is formed. These are tetrahedral void. Okay, and the sphere of second layer are placed above the depression of first layer in the triangular void. So two type of voids are formed in the after placing second layer. One is a tetrahedral void, which is represented by T. Another is octahedral void, which are represented by O. Tetrahedral voids are formed between between four particles or four sphere, and octahedral voids are formed between six particles. Okay, and these two type of voids are obtained after placing the second layer just above, just in the depression of the first layer. Okay, so two type of tetrahedral voids. One is two type of voids are obtained after placing second layer above the first layer. In so first one is tetrahedral void. It is formed between the six particle or six tetrahedral void is formed between the among the four particles. Okay, and these voids are called tetrahedral because a tetrahedron is formed when the center of four sphere are joined, and they have marked as T. And another void is octahedral void, and it is formed among six sphere, six vertical. Okay, and it is marked as O. Okay, so after placing second layer, we get two type of voids: tetrahedral voids and octahedral voids. And you have to remember that if n number of particles are closely packed, if n number of particles are closely packed, there are total number of octahedral void will be also n, and number of tetrahedral void will be 2n. That is, in a crystalline solid, if n number of particles are closely packed, then number of tetrahedral void will be n, and number of octahedral void will be 2n. Okay, that is, the number of octahedral void is always equal to the number of closely packed particles, and number of tetrahedral voids are double of number of close packed particles. Now placing of third layer. While placing third layer just above the second layer, you will get two type of close pack, three dimensional close pack. One is hexagonal close pack, another is cubic close pack. So covering tetrahedral void, you will get three dimensional hexagonal close packing. Okay, and this is like AB type arrangement. So covering tetrahedral void of second layer may be covered by the sphere of third layer. In this case, the sphere of third layer are exactly aligned with those of first layer. Thus, the pattern of sphere is repeated in alternate layer, and this pattern is often written as AB type arrangement. This is in three-dimensional hexagonal close packing, and this structure is known as hexagonal close pack structure in three dimension. Okay, and in this arrangement each particle is directly attached with 12 particle. It is not easy to show the arrangement in two dimensional. Okay, and their actual arrangement is in three dimensional hexagonal close packing is look like this. Okay, and this type of arrangement of atom is found in many metals like magnesium, zinc. And now covering octahedral voids. The third layer may be placed above the second layer in a manner such that the sphere cover the octahedral voids. When placed in this manner, the sphere of the third layer are not aligned with those of either the first or second layer, and this arrangement is called C-type arrangement. Okay, only the fourth layer is placed its sphere are aligned only when the fourth layer is placed its sphere are aligned with those of first layer, and this pattern of layer is often known as or written as ABC type arrangement, and this arrangement is known as cubic close packed CCP or face centered close pack FCC. Okay, so this is cubic close packed, or it is also known as FCC close pack, FCC face centered close pack. And this type of close packing, cubic or face centered, is obtained when the octahedral voids of second layer are covered by the particles of third layer. And here all the a first three layers are different, so this type of arrangement is written as ABC type arrangement. ABC ABC, like this type of arrangement. Okay, so three-dimensional close packing can be obtained from two-dimensional close packing, and you know two-dimensional close packing are two type. One is square close packing, another is hexagonal close packing. And from two-dimensional square close packing you will get three-dimensional cubic close packing. Okay, and from two-dimensional hexagonal close packing you will get two types of different three-dimensional close packing. Another one is three-dimensional hexagonal close packing, which is written as AB type, and another is three-dimensional cubic close packing or face-centered close packing, which is ABC type. Okay, and both in both cases, okay, both this type of close packing, that is cubic close packing or hexagonal close packing in three dimension, are highly efficient, and 74% of crystal 74% space in the crystal is filled. So packing efficiency in three-dimensional cubic or hexagonal close packing is 74%. Okay, and in either of them each sphere is in contact with 12 sphere, thus coordination number is 12. Okay, so coordination number in three-dimensional cubic or three-dimensional hexagonal close packing is 12, and packing efficiency is 74%. Now, calculation of empirical formula. How to calculate empirical formula of a crystalline solid? Okay, here one thing you have to remember, this 3 point. If there are n number of particles n number of particles closely packed, then there are total n number of octahedral voids and 2n number of tetrahedral voids are generated. Okay, and generally anions are bigger in size, so they form close packing, and cations, they are, as they are small, they occupy the tetrahedral and octahedral voids. Okay, so earlier in second section, in this section we have learned that when particles are close packed resulting in their CCP or HCP, two types of voids are generated. While the number of octahedral voids present in a lattice is equal to the number of close packed particles. See this line properly. While the number of octahedral voids present in a lattice is equal to the number of close packed particles, and number of tetrahedral voids generated is twice of this number. In ionic solids, the bigger ions, usually anions, form the close packed structure, and the smaller ion, usually cation, occupy the voids. Okay. Now see how to obtain empirical formula of crystal structure. See example 1.1. A compound is formed by two elements in X and Y. An atom of the element Y as an anion makes CCP, cubic close pack. So Y form cubic close pack, and you have to assume the number of Y atom as n. And those of element X occupy, that cations occupy all the octahedral voids. And now what is the formula of compound? X form close packing. So if number of X is, yeah, number of X is n. Suppose number here it is written the atom of element Y make CCP. So number of Y atom is n. So number of octahedral void will be n. Number of octahedral void will be n. And here it is written the element X occupy all the octahedral voids, so number of X also will be n. So the ratio of number of X and Y is 1:1. Therefore the formula of the compound is X is to Y. Okay, second question. Atom of B form HCP, that is hexagonal close packed lattice, and those of element A occupy 2/3 of tetrahedral void. So you have to assume number of element B in the close packing is n. Then number of tetrahedral void will be 2n, and now 2/3 of 2n is occupied by atom A, element A. So number of B atom is n, you have assumed, and number of element A is equal to 2/3 of n. Okay, 2n, that is 2n by 3, 2n by 3. So the ratio of number of atom A and B is 2/3, two number of A and B is 2n by 3, 2n by 3 is to 1, is to 1, sorry, 2n by 3 is to n, that is 2 by 3 is to 1. Okay, sorry, here it is total number of tetrahedral voids is 2n. Oh, sorry. So number of tetrahedral void will be 2n, 2n, tetrahedral void will be 2n. So number of A atom will be 2n into 2 by 3. So 4n by 3. This is the will be the number of atom, and number of B atom is n. So the ratio between number of A atom and number of B atom is, ratio is 4n by 3 is to n. Okay, that is 4, 4 is to 3. That is the formula of the compound is A4B3. Okay, so you have to practice this type of calculation of empirical formula. Bye students.